So magnetism and inductance, at the heart of magnetism and inductance is this law here, Lenz's law, which, as you see it written in textbooks, says that in any induced current, anytime inductance occurs, there will be a force that opposes the changing magnetic field that caused the induced current in the first place. So this looks really complicated, but once we realise this is a consequence of the law of conservation of energy, which basically says energy can't be created or destroyed, it has to come from somewhere. So if you've got current flowing and a voltage being generated, a potential difference, that's a change in the energy of the system. And where did that energy come from? Well, it must have come from somewhere outside of the system. And so we can say, well, the current that you get or the voltage that you observe is caused by the changing magnetic field because a force will oppose the changing magnetic field. And that force is what makes the current occur or move. And we take advantage of that in lots of different ways. So let's ignore this lengthy, wordy thing and look at an example of, say, a solenoid, which is basically a coil of wire with a number of turns on it, okay? And what we see is that if we take a magnet, so here it is, there's our south pole, our north pole. If we take a magnet and move it towards the coil, what's happening is that because the magnetic field is interacting with the wire, and we know that when charges start moving, that's when you get a magnetic field as well. What you end up with is the coil doesn't like, which is an anthropomorphic thing to say, but we'll roll with it. The coil doesn't like the magnetic field being changed inside it. At the moment, there's no magnetic field. It doesn't want a magnetic field in it. So it will set up an opposing pole. And what you'll end up as a result of that is a current flowing to resist the movement of the magnet. We put force in, we apply an external force to the magnet. Some of the energy that we put into moving the magnet gets converted into providing a responsive force in this magnet here, and that causes a current to flow. And you can see I've drawn on the north to show which way the current flows. However, if we then go on to, with our same coil, and hopefully it's going to look similar, our same coil, and this time the magnet is inside and we're pulling it out, okay? Now the coil has now got a magnetic field inside it. We've forced the magnet in there. We've caused a magnetic field inside the coil. So now the coil doesn't want to change. So when we pull it out, what we get is a south pole. And this time, the current flows in the opposite direction. So a current always flows because it's resisting the change in the magnetic field. So as the magnet moves, or as any part of the system moves, as the magnet moves, there's a changing magnetic field caused by our external force that we're applying, and the current flows, or the voltage is induced to resist that change. And that's at the heart of inductance.